Good afternoon, everybody. So today we shall start a topic that is digital career modulation system. After this, of course, we will little bit of detection before going to the networking. Now, career is typically in electrical domain. It is an high frequency.
Hello, sir.
Yes,
Sir, what is the format of tomorrow exam?
format. It will be
Uh,
problem. Problem will be given. I will have to write the answer.
like numerical, sir.
Numerical.
Yeah, okay, sir. And where the platforms are, whether it is Moodle in MS or
No, MS Forms. It has to. Everybody has to log into Teams. Okay.
okay, sir.
Okay, and there I will give the link for MS Form.
Okay, sir.
So we are discussing about career modulation. Career modulation is typically a high frequency is used as a carrier to shift the frequency bands from the baseband. So that enhances multiplexing as well as noise filtering. Because if it is in the baseband, that is we will have baseband is a frequency range plus minus f around 0. So therefore, if we pass a through a low pass filter to filter out the noise, that will of course filter out the high frequency noise, but the DC offset remains, and DC offset creates problem in thresholding. So therefore, we can write carrier is used to enhance bandwidth utilization and multiplexing. This is the basic purpose. However, it also enhances noise filtering. By shifting a low pass baseband to a band pass carrier band. Typically, digital carrier modulation systems are more or less same like analog carrier modulation system. The message signal is or baseband signal is multiplied to the carrier signal. Similar to analog carrier modulation. So for example, a simplest form like we have in the analog system, we call it amplitude modulation. Here it is called amplitude shift keying. Similarly, there it is phase modulation. Here it is called phase shift keying. And similarly, frequency instead of frequency modulation, they are called frequency shift keying. This is referred to, these are referred as, say, ASK ESK phase shift keying. FSK frequency shift keying. Etc. Like there are QPSK, BPSK, etc. there. So generally, of course, we can have like the analog we have here also, two basic type of modulation and detection. That is, one is coherent, another is non-coherent. Here also there are coherent and non-coherent. From operational point of view, detector, of course, from the detector point of view, there are some difference, circuit design, and of course in the digital domain, digital operation wise also they are different. The basic difference is that coherent means the frequency is known. At the receiver side, carrier frequency is known. So there are certain advantages, of course, if the carrier frequency is known. So then we can do our operations in a better way, like the frequency components can be realized in terms of vectors by taking the dot product of the output signal to the basic carrier frequency. And from that, of course, we can estimate the phases as well. So that is possible. In case of incoherent or non-coherent, not incoherent, non-coherent carrier system, the frequency is not known. So therefore, but however, one thing that is to be ensured in both the systems is that the carrier frequency needs to be separated quite far away from the baseband. Carrier band is frequency is separated from the base frequency. So that will essentially required for separating out various components of or separating out various baseband components around the band. Like say if we have a band of a baseband of 1 megahertz, now this baseband can be shifted to the corresponding carrier band of say both side. It could be depending on this, it could be on this side as well. So if we shift this carrier, say FC equal to 1 gigahertz, now there could be many 1 megahertz, so this is 1 megahertz. Now there could be many such bands that could be placed in this in the carrier band, and then all those signals can be multiplexed and can be transmitted together. So generally, if we take the carrier power spectrum of the carrier modulation in so then we have one band as F plus Fc and another is F minus Fc. So around the Fc there will be two such basebands will be generated. Okay, so that could be shown easily by the simple manipulation of the Fourier transforms. However, in case of coherent, because we are expressing in terms of a known frequency, usually the analysis can be done by in terms of a carrier frequency and its projections onto various phase or other. In general, theta can have a frequency shift or it can have a phase shift. So that is can be projected in terms of an angle change in a multi-dimensional space. So we shall introduce a little bit of signal space analysis to analyze digital carrier signal. Signal space analysis is quite useful. Just we will introduce very briefly about signal space analysis. So signal space analysis is basically projecting any signal onto a particular directions. So just like we have real axis, imaginary axis, we can decompose our signal towards real axis, imaginary axis, or maybe in general x-axis, y-axis, or z-axis. However, these axes can be defined by mathematically, they can also be defined as some function or vectors, or in general by a signal itself. So those signals can be defined as the signal base. So there are, in general, in any signal decompositions or any, we have seen that if the basic primary signals or the base signals are orthogonal in nature, then it is the representation becomes unique. If it is not orthogonal, actually there will be we cannot uniquely define the signals. So in signal space analysis, certain signals are taken as base signal. For example, suppose we are doing this carrier modulation, the carrier frequency signal, that is sine omega ct, if omega c is the carrier frequency, or cosine omega ct, can be taken as a base signal. And any other signals can be decomposed by taking projection along the base signal. By simply evaluating the dot product and the integration. So there are usually, if we also make the magnitude of such projection to unity, then we call that they are orthonormal. For orthonormal signal basis, minus infinity to plus infinity, phi j_t dot phi kt dt equal to 0 for j not equal to k equal to 1 for j equal to k. So if we project a signal phi j_t onto phi kt, then it becomes 0 for j not equal to k. So that means if we take the same components, its product should integration projection should give 1. Now any signal xt could be can be projected along the base signal. Along say phi kt as xt equal to sigma varying k. K can be from minus infinity to plus infinity or could be some number of values, finite number of values. So this is like xk is the coefficient in the direction. We know that various kind of transforms that usually we study like Fourier transform. So there the base signal is a sinusoidal signal, that is phi kt is a exponential basis function, exponential of j omega t. And the coefficient xk is equal to minus infinity to plus infinity xt phi xt phi kt. dt. So as we have seen that just in our last, line coding baseband discussion, that we have represented a band limited signal through a sinc function. It has been observed in baseband. That is the pulse waveform, that's the signal waveform. Can be that a band limited signal can be represented by xt equal to over all values of k xk root 2b sinc of twice pi bt minus k pi. So that means basically we are convoluting with the sinc waveform. Okay. So essentially we are shifting the sinc waveform by this minus k pi function. So writing that convolution of sinc waveform with the coefficient xk, that is the amplitude coefficient ak that we have earlier described as. So that could be the xk, and this is the basic sinc function, and the sinc function is getting shifted and multiplied by those coefficients, and that is being summed up. So therefore that this can be taken as a in general at any position k by k. So that is the phi kt, the base function, and xk is the coefficient. And then we are generating the pulse wave from xt. So therefore, the basic baseband signal can also be interpreted of a coefficient similar to a k used earlier. And xk, of course, also we have seen that the coefficient could be determined that xt, the complete received signal, then if we convolute with sinc waveform, so we will get corresponding to this position of the sinc waveform at k, we will get the coefficient of xk. So this is nothing but 1 by square root of 2b is the bandwidth, x of the sample value k by 2b. So this is the sampled at Nyquist interval. Delta t equal to 1 by 2b. B is the bandwidth. This is of course known as the generalized sampling. So in terms of any bands. So usually this is also known as the band pass sampling. Now this one, once with this small introduction, we can further generalize it with pulse waveforms. Suppose we have now let us take one simple example. So here of course we have taken sinc waveform. Let us, for simplicity, let us take square pulses. So this is say phi 1t. This is phi 2t. Now we have two signals, a signal S1t. The signals are given by, suppose these are the base signal. As you can see, if we multiply phi 1 and phi 2, that is take the cross product, so it is 0 because there is no overlapping zone. And with the signal itself, because the value is 1 and the area is 1, so and if we multiply and sum, that will give 1. So now let us take some signals. Zero, 1, 2. So this is say S1T. Similarly, another signal we have so this is S2T. We can have another this is S3T. We can as well have some scaling factor. This is suppose S4T. So all these signals can be expressed in terms of say phi1t and phi2t in a signal space diagram. So if we have the two axes as this is phi1t and the orthogonal direction is phi2t. So S1 would be say both 1 1 is minus 1, of course. So this is S1. It's just like vector. Signal space diagram is like vector. Now S2 we have this one is minus 1, and that one is plus 1. This is S2. Similarly, we can have S3, S4. So S3 we have one is phi1 is 0, and then that one is minus 1. this is S3, and for S4 suppose this value is 0.5 and this value is 1, so this could be, this is 0.5 and that value is 1, so this is S4. So this way we can, in terms of two orthogonal functions or multiple orthogonal functions, of course we can represent in various signals. I think we will continue our discussion further, most probably next day. So we shall discuss the coherent digital carrier systems first. So we will start with coherent binary phase shift keying. So phase shift keying means the information of the symbols are embedded in the phase. Coherent binary phase shift key. The information of the symbols of 0 and 1 are essentially embedded in the page. And because it is coherent, so we know that omega c or fc, that is the carrier frequency. The two signals representing the two binary symbols are by the phase difference representing are given by √2 EB by TB cosine of E is B is the energy and TB is the duration. And the √2 is the factor is coming because the energy is associated with RMS value. So that way √2 factor is coming. So one symbol could be where phase is 0. Another symbol could be represented by √2 EB by TB cosine of twice by FCT plus pi, that is the pi phase difference. So both are of course defined for 0 less than equal to t less than equal to TB. That is for a period of TB, capital TB. So one basis function of course is root 2 by TB cosine of twice by FCT, and another so with that, of course, we can represent both. So S1t is equal to square root of EB phi 1t (0 less than t less than equal to TB), and S2t also we can represent, because basically same frequency, minus square root of, because of the pi we are treating as minus phi 1t. If we take S11, that is the projection of value of the signal S1t onto phi 1t. So that will be, the coefficient is S11, that is 0 to TB, because we have defined these signals up to TB, S1t phi 1t equal to plus square root of EB, S21 0 to TB, S2t phi 1t dt, equal to minus square root of. Now if we represent this one in a signal space, I think we will discuss it next day. Just I am drawing it. So we have only one here. There is no other function necessary for PSK, binary PSK or BPSK. Only one is sufficient. So therefore, one point will be square root of EB, and another point is minus square root of EB. Both are on the x-axis, that is in the direction of phi 1. So there is one zone called region 1, that is Z1, because this square root of EB is a positive zone, and region 2 Z2. So the decision for having 0 or 1 can be taken on this boundary. So this is the decision boundary. Now accordingly we can define the observation measure, and correspondingly we can define transmitted message, receiver, and the probability of finding 0 as 1, 1 as 0. All those things we can find. So by defining an observation measure, I think I shall stop, because tomorrow is the exam. One can find the error probabilities corresponding to this decision. All right, let us stop here.